So assume I was given two vectors, my vector A and my vector B. Scalar products at the end of any multiplication of two vectors, any two vectors you are multiplying, if it's a scalar product, the value is going to give you is not going to be a vector quantity, it's going to be a scalar quantity. That is what made it a scalar product. So if I'm trying to multiply these two vectors scalarly, if you are multiplying it, at the end of it, the value you are going to get is going to be a scalar, it's not a vector. But if it's a vector product, I'm trying to vectorize it, that is, I'm trying to product them vectorly. At the end of it, the value I'm going to be having is going to be a vector product. So let me show you an example of it. Assuming I'm trying to scalar product this stuff, I'll be having this as my answer. Remember, this A has three values: A of x, A of yj, and A of zk. So I'm trying to dot it with my B of xi plus B of yz plus my B of zk. So this is the way you normally do a scalar product. So if I'm trying to produce this thing scalarly, take note. Anytime you are doing scalar product, you'll be using your rectangular unit vector. You'll be placing your rectangular unit vector in mind. So if you are placing your rectangular unit vector, here is my j now. This is my j. This is my j. This is my x, and this is my z. This is my k rather, because this is the z axis. This is my x. This is my y. So this is my j. So you'll be taking your rectangular unit vector in mind. Anytime you are adopting an I and an I, or a j and a j, or a k and a k, the value is going to give you at the end is 1. But if you are doing an I and a j, I and a k, or a j and a k, this value they are going to give you 0 at the end. So if I'm trying to dot get the scalar product of this vector, I'll be multiplying my a of xi with this b of x, and normally my I and I will give me 1. Take note, it's only when you are dotting your I and I, j and j, that you'll be having a definite value. The remaining ones, they are going to give you 0 at the end. So you'll not be having your dot product of a So using that rule I just gave you, my a of x, my b of x, plus you are dot producting. Scalar product is also known as dot product. So you are dot producting our a of x and my a of b. This is what is going to give you. My a of y and my b of y. It is going to give you a of y, b of y. Then my a of z and my b of z. A of z, b of z. If you look at this value, like I said, since it's a scalar vector, the value is going to give you is going to be a scalar product. This is a scalar product. Rather, this is a scalar value. So when it now has to do with the cross product, when it now has to do with the cross product, I'm trying to cross product two vectors. Take note, if you are cross producting any vector, we are going to be using the determinant method. So my a of x, a of y, a of z, b of x, b of y, my B of Z. So I want to now cross product it. So my value, the value is going to give me at the end of this is my I into bracket. If you are to cross product the I, first of all, this part is going to be hidden. You'll be left with this part. Then we have to find the determinant of this, which will be my AY times my BZ. AY BZ minus AZ BY. Take note, the cofactors for these vectors is positive, negative, positive. So my minus J now, my minus J value, if you are to make the middle part hidden, you'll be left with this guy and this guy. So if you are cross producing it, the leading diagonal AX BZ, AX BZ minus my AZ BX. Then for the last one, my K value. You are going to make this part hidden now. The K part is like you doing an L towards that part. So what will remain is just this part now. So if we are trying to get the determinant for this part, it will be AX BY. AX BY minus AY BX. So this is normally the cross product of any two vector. Then we will not talk. We will not be making mention of the derivative of a vector. We are going to look into that part broadly. How do I get the derivative of it? The major why we mostly get the derivative of any vector is in order for us to change a quantity that is being ratioed with time to another quantity that is being ratioed in time, majorly in vectors. So if my displacement, first of all, is having a value in time, I can then differentiate it. Differentiating my displacement gives me my velocity, and differentiating my velocity gives me my acceleration. Then if I'm trying to integrate my vector, any vector I'm given, I'm told to integrate it. Anytime I'm integrating that vector, assuming it was initially an acceleration, if I integrate it, it's going to give me a velocity, and if I integrate my velocity, it's going to give me a displacement. So that is how the ratioing of this derivative of this vector is. So let me show you, let me give you a pictorial view of what I've been saying since. For the derivative of the vectors, so this is a vector. The vector is being ratioed with time, first of all, and it gives you A plus take note, majorly, it might not be the time that you are using to rate up your velocity, your vector. It might not be the time you are using to rate up the vector. It might be anything. It can be displacement, it can be other values outside time. So if I'm told to get the derivative of this vector, it's going to be so this is how you get the derivative of a vector. So let me just give you an example of it so you try and get what I'm trying to say. So assuming assume the value we're given is a vector. Let's assume this is a vector. 3t squared I plus 2tj plus 3t3k. So we're told that this vector now is the displacement of the vector, and we're told to calculate for the velocity of it. So if I'm trying to get the velocity, to then give you 9t squared. Now to differentiate now. Normally, how do you differentiate any vector? Multiply our 2 by our t, subtracting 1 from the 2 on top. So I didn't subtract my 1. So 3 times 2 is what? To give you 60. Subtracting 1 from that. Take note, if you are differentiating any vector, it will not affect the value for your I, j, and k, the coordinates. It won't change the coordinate. The coordinate will always remain the coordinate which is 6. So our 2t, if we differentiate it, 1 times 2 is 2. Then 1 minus 1 is 0. So it will now be 2. Plus, if you differentiate this one, it will give you 3 times 3 is 9t squared. So that is that under this part. Then how do I integrate a vector? In order to integrate a vector, the same thing goes with the differentiation and the integration. They're almost the same thing. This is the vector now, t2, t1. This is the vector. So we're told to integrate it. Remember, it's a vector. So if you are integrating the a of x of t, so this is the way you integrate it. You are going to do the integration simply to the coordinate axis. You will transfer the integration factor both for the x-axis, the y-axis, and the z-axis. That is that under any value of integration you are trying to do. You are trying to integrate it from our acceleration to the velocity, and from our velocity to the displacement. So let me just give you like that example I did just now. I'm not sure I'm going to create a calculation on this part. So assume the value we have is 3ti plus 2t squared j plus 3tqk. I remember you were told that the vector here is the displacement, and we're told to get the value for the velocity. How do we do it? We want to rather this is the acceleration of the vector itself. The acceleration is already given. We're told to get the velocity. You have to now integrate this guy. So if I have to integrate the whole of this stuff, how do we do it? We're not giving a boundary value for our t. Assuming we're giving a boundary value, we can just use a boundary, but I don't want to introduce boundary value here. We'll be wasting our time. So if I'm trying to integrate this value now, it will give us 3t1 plus 1. What you do at the top, you do it at the bottom. 1 plus 1 plus 2t squared j 2 plus 1. Remember, this is your I, all over 2 plus 1 plus 3t cube plus 1 q plus 1. Okay. So if you are doing it, you'll be having 3t squared over 2i plus 2t cube over 3j plus 3t raised to the power 4 over 4k. Remember, the major reason why we are having the value this way is because I figured out the question for my head. So this is just that under the integration of any vector. So I'll be talking elaborately now on the divergence, the grad, the call of any function where we have a Laplacian operation and a Laplacian operation and a Laplace equation. So first of all, let me talk about the grad function. The grad, assume this a scalar potential function. A scalar potential function, they are represented by x, y, and z. This is the normal way of it has both s, y, and z, but they are produced in three form. I'll give some example under this part so you understand it very well. So the grad function is trying to tell you the gradient of the phi. That is gradient. Gradient is the same thing as the differentiation of any function. Gradient is the same thing as differentiation of any function. If I'm trying to put that will involve me introducing mathematics here, but we don't need that. So let's get the gradient from this function. If you're trying to get the gradient for this function, we will be differentiating x, y, and z implicitly. That is towards the axis where x is, towards the axis where y is, and towards the axis where z is. So the differential of the xi plus the differential of the yj plus the differential of the zk. This is the grad function. The grad function is also written. It can also be written by can also be represented by this operation called the del operation. Operator, which is also known as a differential operator. So this is that under the grad function. So at some point in time, they will multiply two gradient function together. If you multiply any two gradient function together, this is the gradient function. You are trying to multiply two of it together. It will give you a Laplacian operation rather. So remember, I'm dotting it. I'm doing the dot product here. So if you are dotting it, so if you are trying to dot these two products, just like the way I did that first dot product format, you will just be interested with this one. And this one multiplying, these two multiplying itself, it will give us the square of it. So our v prime square is equal to, our v operator square is equal to our sigma over sigma x square plus sigma over sigma y square all squared plus sigma over sigma z squared. This operation is called a Laplacian operation. This is what is called the Laplacian operation. Then when this operation is multiplied by the scalar potential function, like I said, it will give you, and it gives you 0. What the type of equation or the type of function that is formed at that point of time is called a Laplacian equation. I don't need to write that. I don't need to do that. So the kind of equation that is formed at that point is called a Laplacian equation. Then I will now be talking of the divergence of a vector A. How do I diverge a vector? if I'm trying to diverge any two vector, divergence of a vector A, then I'll be multiplying, I'll be deducting my delta operation with the vector itself. So the I sigma over sigma x plus j sigma over sigma y plus k sigma over sigma k, or rather plus k sigma over sigma z, dotted by our a of xi plus a of yz plus a of zk. So this time I'm trying to dot these two together. Remember that our I and I is the part we are interested in. If you are trying to dot any two operation together. So this guy will multiply this guy, will be having our divergence of A to be equal to our sigma over the sigma x, A of x, plus our sigma over the sigma y, A of y, plus the sigma over the sigma z, A of z. So this is the normal format for the divergence of any function. This is the normal format for it. Then outside the divergence, we'll be talking about the call of a vector A. How do I call a vector? Call is just like, since we have scalar vectors and a scalar product and vector product, we did grad function dotted. We did the grad function dotted by A, giving the grad function dotted by A, giving the divergence of A. Then this time we will not be dot producting it. It's now like doing the vector product. We are now doing the grad function, that is our V, crossed by our A. It gives us the call of any vector. And remember, anytime we are cross producting, like I said, we'll be doing it using the determinant format. Said anytime we are cross producting, the normal format which you usually use in solving that kind of cross product, will be using the determinant format. Determinant format is this stuff I'm trying to create. So if you are trying to cross product these two vectors now, our I will be giving us, no, I don't like stress, so we'll just simply cut this part out. We cut this part, we'll be left with this part. And if we are cross producting, you'll be having sigma over sigma y, A of z, minus, remember it's the leading diagonal we pick first before picking the other one, minus the sigma over sigma z, A of y, minus j brackets. This is now the format for the j. The sigma over the sigma x, A of z, minus the sigma over the sigma z, A of x, then plus our k. Remember I told you the cofactors for this is plus, minus and plus. This is the cofactor for it. Then for the k part, the k operation, you sabotage the k part. You'll be having just this part left out. So if I find the determinant, we'll be having k bracket the sigma over the sigma x, A of y, minus the sigma over the sigma y, A of x. So that is all we have under the call of any vector. So I want to explain some few things under the call of a vector. Take note, whenever the call of a vector is equal to 0, whenever the call of a vector, like whenever you are cross-producing the gradient of any function by the actual vector of the vector itself, anytime you are cross-producing it, when it gives you the call now equals to 0. At that point in time, we are going to say that vector itself is conservative. Conservative means that it's the energy, or conservative, for something to be conservative in general format in physics and mathematics and everything, it means there's nothing lost, there's no kind of loss attached to it. Energy is not being displaced in any format. So at that point in time, our A is going to be ascribed this value. Whenever our call of any vector is conservative, our A is going to be ascribed this value. Our A is equal to minus V, the delta operation of any vector, times the gradient, the scalar potential function. So it will now be equal to A is equal to sigma over sigma r. Take note, this sigma over sigma r is just the general form for writing the three components. If you don't want to stress yourself by writing sigma over sigma a, sigma over sigma y, sigma, now adding the three together, representing it in the vector form, you can just pick a short form, or the short notation for it, the sigma over the sigma r. That tells you already, you are already talking about the three vector. So if you want to now list the three vector of it, that is your own part of it. It doesn't really matter. So if you are trying to get the value for our phi here, in case we are told to, in case the question asked us when the system is conservative, we are told to calculate the value for phi. Our phi here, our sigma phi minus sigma phi, is equal to our A sigma r. Take note, whenever a system is conservative, our sigma phi would then be equal to minus A sigma r. Take note, these functions are both differential functions. So I stopped here. Let me just write it here. Our sigma phi is equal to what? Minus A sigma r. So this is it. Remember I said this is the differential of this form, our phi, our scalar function, and the three quantity x, y, and z components being placed in one, giving the value r. So in this format, our d phi is equal to minus A. You are changing this one now to the differential of phi, is equal to minus A r dr. Look at this part very well. I changed my dr to r dr. This is the way you do it whenever it's conservative. So in order to get my phi normally, I will have to integrate. Remember, this function is equal to this. So in order to get my normal phi value, I will have to integrate the whole of it, minus A r dr. So our phi is equal to minus A integral of r dr. So that is that under this video. I think this definitely will help you solving any questions under vectors. You don't really need too many questions now, because you don't really need too many solvings. Just this explanation in I believe you can solve any question under vector. So that is that under the vector aspect of, that is that under scalar and vector quantity. Thank you very much.